Hi, everyone. My name is Chase Douglas. I'm the CTO at Stackery. Stackery is a product that helps customers, companies build, manage, deploy, and monitor their serverless applications. And as we've helped many of our customers go through their journey along serverless, we've noticed many patterns of challenges that they face. And I wanted to talk about a few of those today to give some insights. So we're looking at serverless solutions for non-serverless problems. And each of these are examples of problems that demonstrate a category. The first one, working with SQL databases, is about how you might need to interact with non-serverless resources and what that can mean. The second one, rate limiting. We actually just heard a talk all about that from Dana. We're going to expand on that a little bit in some different ways. And the third is state machines, where we're going to look at how you can incorporate complex logic into an application. So let's start with working with SQL databases. And again, this is an example of how you might have to do some things differently when you're trying to interface with non-serverless resources. Let's start with a scenario. Pointy-haired boss comes to you and says, you need to build an API that accesses data in our MySQL database. And you think to yourself, well, this isn't too hard. I know how to do this. We can do it. We just are going to add our favorite ORM and database driver to our function code, connect to the database, query, and then profit. What could be so hard? In fact, AWS, as an example, shows you some Python code showing you how to connect to your MySQL database so you can query it every time your handlers run. Easy peasy. Except that there are dragons lurking around the corner that will flame you as soon as you run this in production at any sort of scale. So you push this out to production, and your users start to come back to you and say, hey, wait a minute, I'm getting these errors, something about too many connections. And you wonder to yourself, what's going on? I'm going to go check on our throughput, and I don't see any crazy throughput spike going on. But I do see a spike in our error rate. So let's figure out what's going on. We're going to start from the opposite side of this problem, which is what is the underlying problem here? And that is that most SQL databases are not serverless friendly. Generally, they do not scale horizontally. And we know that in some ways, in terms of storage and CPU power, databases often don't scale horizontally. But in this case, it's actually about network connections, which is something you don't usually have to deal with when you're dealing with a non-serverless approach. You have a certain number of servers, meaning a certain number of connections, and you'll never go above those. So why do databases have this limitation in the first place? Well, every connection to that database is handled on an independent thread of execution. That's great for parallel processing, fully utilizing the server that it runs on. But each thread requires memory set aside to maintain its state, like its current stack and thread local storage. And it's expensive to swap between threads, so you can end up in sort of a resource starvation if you have too many threads at any given point in time. So the problem here, if we go back to our code, is that when we're running our functions, after they've run, that connection to the database still exists, even while the function is sitting idle. Let's look at an example of how this can be problematic. Imagine you've got an API service. It's running with 5 endpoints, 5 functions, one for each endpoint. And you know that this service runs at 100 concurrent requests, and it never goes above that. And you also know that your database can handle 120 connections concurrently. So how can this be problematic? Well, we know, first of all, that each function that has idle instances are holding open connections to the database. So now let's take an example. Let's say that across our API, we have even traffic, 20 requests concurrently for each of our functions. So in total, we're only using up 100 connections to the database. But now let's imagine that in the next minute, list users, our first endpoint, spikes to 40 concurrent connections, while every other endpoint goes down. So we're still at 100 concurrent requests to our API, but because those other scaled down functions still have idle instances that are open, that have open connections, we're now reaching our limit for our connections on our database. In the next minute, let's say that getUser now is hit 40 times concurrently, and all the other functions are not hit as much. So we're still at a throughput to our API of 100 concurrent requests, but now we've busted through our database connection limit. Your service is, at this point, fallen over. So what can we do about this? Well, the easiest solution is just to wait, because the cloud service providers are great at solving these kinds of problems. In fact, just like a knight in shining armor, AWS has announced, and it's in private preview, the Aurora Serverless database, which is a horizontally scalable MySQL and Postgres compatible service. And in particular, it has no network connection limits as it scales up. But that's not a practical solution for the challenge of connecting to an existing MySQL database. There is another solution, and it's pretty simple. Instead of creating our connection as the function is instantiated, we can just create it every time our function is called, and then destroy that connection when the function finishes. Now, this is so simple, and you're probably thinking to yourself, wait a minute, why is this not the standard way of doing things, or at least the way that AWS in their example might suggest? And there are reasons. This might add overhead on every call, every invocation. It does add this overhead, but you've got the tools at hand to measure how much it is. And you may find that the overhead is perfectly within reasonable limits for your needs. From our own experiences, we've seen that the overhead of connecting to a database within the same AWS region as the Lambda functions adds about 10 milliseconds in connection time. Now, depending on your use case, that may be trivial, it may be too much, but there are solutions to get around this issue. So now that we've talked about connecting to databases as an example of how once you start to interface with non-serverless resources, you can hit problems that you never experienced before, let's look at a different example, in this case rate limiting, of how you may need a serverless solution in absence of something you might assume comes along with your functions as a service platform. Again, we'll start with a simple scenario. Your marketing department has syndicated out a bunch of content. They do a great job of this. And now they want to evaluate how their content is ranking out in the real world. So they come to the engineering team, and they say, can you please go out, scrape the pages for all our partners, and find out where our content is ranking? And you say, yeah, sure, we can do that, but we're going to make sure that we're good net citizens. We're going to add some rate limiting so that we're not harming our partners. So what does it mean to have a rate? I mean, at a simplest example, we're talking about a quantity of something over a unit of time. In this case, page requests per time. So let's look at our example in a little bit more depth. We decide that we want to only hit our partners at about 60,000 times per hour. We can divide that out to get a more granular amount, 1,000 requests per minute, which makes it a little bit easier to develop and test. And so we need a solution that every minute is going to scrape 1,000 pages. one mechanism we can use as part of this, we need a way of having a way of invoking a bunch of these requests each minute. So we need a heartbeat generator. So this gives us a consistent interval to ensure we have a steady rate. And thankfully, there are solutions for how to create a heartbeat generator for all the major cloud providers, some easier than others, but they all have templated capabilities for this. But then you think to yourself, well, 1,000 requests every minute is actually a lot of requests. I don't know that a single Lambda can actually handle that. And you're probably right. And you realize we need to add some concurrency into this as well. So how can we add all this together? Well, after we do some measuring, we realize we can safely do 20 page requests each minute per function that we invoke. So that means we need 50 concurrent function invocations every minute. Well, let's look at one example, one solution to this problem. We can trigger functions manually. So here, every minute, we have an invoker function that goes out and grabs a list of 1,000 functions, or 1,000 pages to scrape. And then that invoker can now invoke 50 instances of our scraper function with 20 pages in the input message each to go and scrape. And this is a great approach for a couple of reasons. It's very configurable. You get to decide the batch size and the concurrency that you want to run at. And it's also very inexpensive. You only pay for the amount of lambdas that you invoke, the amount of functions. But there are some downsides to this. And the main one is that there's no great retry capabilities built directly into this system. It's possible that your invoker function, if it invokes the scraper synchronously, it can find out if the scraper has failed, and then it can re-invoke it. But your invoker function can only live at maximum for up to 5 minutes in the case of Lambda. Alternatively, if the invoker function invokes the scrapers asynchronously, if they fail, they'll be retried, but only a set number of times. And then after that, the failures are just dropped. So let's try to add some retry capabilities to this. We can do this by adding something called a fillable queue. It contains a specific amount of work that's needed to be performed at the moment. And it's also got the property that it's retriable. If any particular amount of pages that we want to request fails, the record for those pages remains inside of the queue until it succeeds. And thankfully, it's very easy to provision these. There's lots of solutions out there, from queuing services that are serverless in nature to utilizing databases or Redis cache clusters. You may already be using those for your solution, so you can build on top of that. So let's start looking at another example, another solution using a fillable queue. Here we're going to try using partitioned queues, such as AWS Kinesis Stream or Azure Event Hubs, which are very similar to Kafka, if you're familiar with that model. The way we're going to provision this is we need 50 functions that run concurrently. So we're going to provision the queue with 50 partitions, because each partition invokes one instance of your function. Every minute, we have a fill queue function that is going to take 1,000 pages from our list of pages, and we're going to add it to our fillable queue. And that's going to spawn off 50 functions in parallel, one for each partition, with about 20 pages each. So this is a great solution technically. It adds in our retriable capabilities, and it's very configurable. We can set the batching size, we can set the concurrency rate. But there's a significant drawback to this approach, and that is that it's expensive. You have to pay for each partition that you provision. In the case of AWS Kinesis data streams, it's $10.80 a month for each partition to exist. And that may be more than you want to budget for this particular project. Let's look at another solution that may kind of bridge the gap. We kind of want a stream system, like the previous solution. Well, in fact, you can get that sort of for free, or at least very significantly cheaper, by using a key value storage system that happens to have a stream attached to it. In this case, AWS DynamoDB and Azure Cosmos DBs are great solutions. As you add records to them, they spawn off messages onto this stream that can then be connected directly to invoke a function. So the way this works is every minute we're going to add 1,000 pages to our key value store. Each page is batched into 20-page messages that then invoke the scraper function. The only problem is that concurrency, while it is possible, is not configurable. You can't ask the service to spin up X number of streams coming out of the database. You can only let it configure how many streams it thinks you should have. So the pros of here, we still have retriability, and it is still somewhat configurable. We can set the batching size, that the rate at which messages are put together into one message to invoke a function. And we also have the side benefit of queue visibility. We can peer into our fillable queue, because it is a key value store, to see what work is still left to be performed at the moment. But the downside is the concurrency rate is not configurable. So you have to do some extra testing to see if this solution will really work for your use case. And it's much less expensive generally than the pure streamed provision partitions approach. But you are paying based on provision throughput for the key value store. So it's not quite as cheap as just spawning things directly using functions. So which should you choose? Well, if errors are not a big concern for you, you just want a best case effort, then you can use a spawner function like in solution 1. If you need precise control over batching and concurrency, and cost isn't as much of a concern, then using a partition queue approach is a great solution. If you are cost conscious, though, and you need retriability, you can investigate using a key value store, and if that fails, you can put more effort, development side, into handling errors using maybe dead letter queues or some kind of other approach to siphon errors off and retry them. It just requires a bit more special effort. So that's a good example of how you might need to use serverless resources to build something into the serverless platform that you kind of expected would be there already. Let's look at a third example of what you might need in a serverless application, and that's state management. This is an example of how you might need to bring non-serverless approaches into a serverless world. So when we're talking about state management here, at least what I mean here, is the ability to encode the logical steps that your application takes into a coherent, both diagrammable form, but also encodable form in a declarative nature. So this is an example of a state machine. Now, you don't have to read what's on here, but you can just look and imagine that every colored oval is a state in the machine, and a state is represented in a serverless application as a piece of function, a function itself that may need to be invoked. And then the output of that function, the result, is evaluated to figure out what is the next state that needs to be invoked. So this is the functionality that we want to be able to build into our system. You need two key mechanisms to be able to do this. The first is that you need concurrency coordination, the ability to tell that if a state requires, say, 10 functions to be invoked concurrently, the 10th function needs to know, I'm the last one, and so I need to evaluate the state of the state machine and transition to the next state. You also need support for state transitions itself, the ability for a function to know what part it is in the entire system and how to decide what is the next state to invoke and how do I invoke it. If we have these two capabilities, we can implement any sort of state machine logic in a serverless application. Let's first take a look at how we might build concurrency coordination. What it requires is external state, because when you're running inside of a function, you actually don't know what other functions may be running, even of your same instance. You don't know if you're that 10th instance of a function, and when you're done, you're the last one. So you need to use some kind of external state. As an example, I'm going to talk about what Stackery does when a customer wants to deploy a stack that has, say, 5 functions in it. We have a splitter function that looks at the stack, sees that you have 5 functions, and it knows it needs to prepare 5 of these. So it's going to add a record to a database table, like a DynamoDB table, that says, we're going to invoke 5 builder functions. Now we're actually going to invoke those builder functions, one for each function that we need to prepare. And after each of these builder functions completes, it's going to go and decrement the number of invocations in our functions table. And we can check now if there's no more invocations remaining, then we must be the last one that succeeded, so we can transition to the next state. Let's look at the other mechanism that we need. State transitions. And to do this effectively, we need some kind of local state. The local state that we need, we are often used to building in as logic of our app. If condition A, invoke function X, else invoke function Y. But there are other ways of using local state to encode how your function is going to move on to the next step. Let's look at our function building example again. We've got our splitter function, looks at how many functions in a Stackery stack need to be built. And it invokes a builder for every one of those functions. But maybe that builder fails. One of the steps that we do as we're building your function is we install all of your dependencies. So if it's a Node.js function, we run npm install. If it's a Python function, we run pip install for all your dependencies. Sometimes those external services fail, and we want to have some kind of resiliency in our system. So when a failure occurs, we can look for a retries property of the message that we were given. Now, at first, there's not going to be any property there. So we can assume that we've had 0 retries. Now that we've failed, we're going to check to see, have we gone past the number of retries that we're allowed to perform? So if there was a retries property on that input message, say it says we've retried 3 times already, and we only allow ourselves to be retried 3 times. Now we need to move into a failure state. If we haven't reached the maximum number of retries, then we can add the number of retries into the input message, incrementing the count as necessary, and we can re-invoke ourselves to start it over again. So this is a mechanism by which we are maintaining local state as part of the input message into a function itself. So this is all great, but we just looked at 2 examples that were very specific to how Stackery builds functions. Can we find a way to make a more general approach to this? A lot of us know of 2 services that do this, AWS Step Functions and Azure Logic Apps, and they are great at letting you build a complex state machine that invokes functions and deals with all of these issues. except that there's one key problem, and that is they were built for one type of use cases, mainly business process logic, things that need lots of auditing, and that maybe entail state machines that might last up to a year in length. And that has driven up the cost of these services. So unfortunately, they tend to be too expensive for high throughput applications. There's another approach, Ben Kehoe. How many people, by the way, know Ben Kehoe? He is like a giant in the community and also like tweets prolifically about serverless. He has this amazing project that he started on called Heaviside. Heaviside is his attempt to build compatibility with AWS step functions by providing the information about the state machine as part of the context that is invoked with a Lambda function. Unfortunately, the context mechanism doesn't work for asynchronous functions. So after he got through all this and tested it out, and it's all working for synchronous stuff, he realized that it breaks down because you can't asynchronously invoke functions in Lambda with context. But that was just the mechanism that he started with for inserting the state of a system into a function invocation. It is possible to do the same thing using an input message. They're part of the input message itself. And this is sort of take-home homework in a sense. Unfortunately, this isn't a fully fleshed out solution yet, though it shouldn't be too hard to drop in for Heaviside. So my goal today was to talk about some of these common patterns of serverless issues, or at least challenges that customers that we've had who have gone through this journey of building their serverless infrastructure have hit. We've seen an example of how you can hit different types of problems than you've never seen before when you have to interface serverless and non-serverless resources. We've looked at how you may need to add rate limiting as a fundamental piece of your architecture using serverless resources. And we've looked at how you may want to build in more declarative logic for your application using state machines. So my hope is that going through this, you gain an understanding that even when you see non-serverless problems, that there are often serverless solutions to them, and you feel empowered to solve these. So hopefully you can now go forth and do more with serverless. So thank you. My name is Chase Douglas again. I'm the CTO at Stackery. If you or your projects or your company needs any help in productionizing your serverless applications, Stackery is a great solution for that. In fact, all the diagrams that I showed of how to wire functions and resources together, that all comes out of our application where we help you lay out and design how your infrastructure works, and then provide monitoring on top. A lot of that observability that everyone is focusing on is very key to having a production-capable system. Feel free to email me, find me on Twitter as well. So thank you.